Thank you very much. It's an honor to be able to speak at the Future Science Prize Symposium. I am going to talk about Trustworthy AI. I am the Executive Vice President for Research and Professor of Computer Science at Columbia University. I'm also an Adjunct Professor of Computer Science at Carnegie Mellon University. The talk I'm going to give on Trustworthy AI is divided into two parts. The first part, I'm going to explain what I mean by trustworthy AI in the context of trustworthy computing. And the second part of my talk, I'm going to propose one way in which one could try to make an AI system trustworthy. And that way is using formal methods. It's just one of many ways that we might want to make an AI system trustworthy. So let's begin. We already know that for certain tasks, AI systems have achieved human performance. We can recognize objects in the street. We can recognize speech at our home. And in certain tasks, AI systems have exceeded human performance. So as many of you know, AI systems have beaten the best human Go player in the world. And the same is true for many other games. The promise of AI is huge. They will drive our cars. They will help doctors diagnose patients better and more accurately. They will help judges make more uniform court decisions. And they will help employers find the most suitable job candidates for their positions. Of course, the most exciting advance in AI occurred very recently, and that is with large language models, or more generally, generative AI. And we already know the potential of large language models of helping everyone in whatever job they do, for summarizing information, for creating new information, and for helping humans do their job. But there's a big question. Why should we trust AI-based systems? If we add duct tape to a stop sign, we can fool an image classifier into saying it's not a stop sign. If we add noise to an image, they classify a benign skin lesion as malignant. We also know from studies that have been done by the media and academia that AI systems that are used in the US court system can be racially biased. And we have heard, also reported in the media, that companies that try to use AI systems for hiring decisions have been biased against women. And of course, we also know that this wonderful technology that emerged in the past few months, generative AI, large language models hallucinate. They confidently invent information that's not true. So the question is, how can we deliver on the promise of the benefits of AI, but address these scenarios that have life-critical consequences for people and society? In short, how can we achieve trustworthy AI? And now I'd like to put the term trustworthy AI in context of a term that the computer science community has been using for decades, called trustworthy computing. Trustworthy computing has come to mean certain properties that we would associate with a computing system. Trustworthiness for a computing system means reliability. Does it do the right thing? Safety. Does it do no harm? Security. How vulnerable is the system to attack? Privacy. Does it protect a person's identity and data? Availability. Is the system up when I need to access it? And usability. Can a human use the system easily? And by computing system, I mean a piece of hardware, a piece of software, and the people who might use the combination of hardware and software. For trustworthy AI, we're raising the bar in terms of what we mean by trustworthiness. Of course, we want a trustworthy AI system to be trustworthy in the sense of traditional computing systems. We want AI systems to be reliable and safe and secure and so on. But trustworthy AI adds new properties of trustworthiness for us to consider. Accuracy, robustness, fairness, accountability, transparency, interpretability or explainability, and even ethical questions. And AI systems also are a little different from the kind of computing systems we've focused our attention on in the past. In particular, one can think about an AI system as not just a piece of code like the machine learned model, but the data that was used to train and test the code, and the data on which the model is going to be deployed in practice. And then for many AI systems, as I alluded to in my opening remarks, there's a specific task that the system is supposed to perform. So one can think about an AI system as everything a computing system is, plus data and specific task. Now, what about these properties I've just introduced? Accuracy is perhaps the gold standard for machine learning. How well does the AI system do on new, unseen data compared to data on which it was trained and tested? Robustness. How sensitive is the outcome to a change in the input? Fairness. Are the outcomes unbiased? Accountability. Who or what is responsible for the outcome? Transparency. Is it clear to an external observer how the system's outcome was produced? Interpretability or explainability. Can the system's outcome be justified with an explanation that a human can understand or that is meaningful to the end user? And for ethics, was the data collected in an ethical manner? Will the outcome be used in an ethical manner? And ethics is a very difficult property to strive for an AI system, because ethics may be culturally dependent. It may be locally dependent. It may be dependent on a community. So whether a question should be answered yes or no may differ depending on who you're asking. And even properties like fairness are not easy to define formally. And there are many notions of fairness that have formal definitions, but are actually in contradiction with each other. So these are new properties that we have to worry about when talking about trustworthy AI. And they're challenging properties to formally define. But these are the kinds of properties end users want of AI systems. And businesses, the customers for any company will want AI systems that that company produces to be trustworthy in these manners. So the question I pose the community, the computer science community, is how can we achieve trustworthy AI? One approach is through formal methods. So I want to now put into context traditional ways that one might use formal methods to verify a computing system satisfies trustworthy computing properties, with how we might interpret that framing for an AI system with respect to trustworthiness properties for AI systems. So let's start with traditional formal verification. There are three components in the red box. It's read M satisfies P. M stands for the system, the AI system or the computing system that we want to show satisfies a particular trustworthiness property. M could be a piece of code, could be a program, or it could be a high-level protocol specified like as an algorithm, or it could be an abstract model of a concurrent or distributed system. In the end, M is a mathematical object. We can reason about it, we can manipulate it, we can build these objects to scale so that we can automate our reasoning about M. P stands for the property of interest that we want to show of M. P will be our expression of the trustworthiness property we care about. It could be a security property, a reliability property, availability property, and so on. And many decades of research have gone into just the ability to express P and to classify the different kinds of P's we can express in different kinds of logics. So P's usually written in some kind of discrete or Boolean logic, and the kinds of properties we care about for verification are usually divided into what we call safety or liveness properties. So reliability is a safety property. Availability is a liveness property. And finally, we have the double turnstile symbol, which is read as satisfies from mathematical logic. M satisfies P. Satisfies, this double turnstile, connects the model M with the property P. It really can be viewed as a logical framework for reasoning about whether M satisfies P, whether the property P holds of every execution of M. And again, decades of research have gone into inventing logics so that we can do this reasoning, building computing tools so that we can do the reasoning automatically and to scale. And the kind of tools I'm talking about are model checkers, theorem provers, and satisfiability modulo theories or SMT solvers. Now, very often, we also add a fourth component in our reasoning for traditional formal verification, and that is what I call E. E stands for the environment in which the system, represented by M, will operate. So you can think about E as the physical environment in which you put the computing system, or you can think about E as the operating environment, like the operating system, for a piece of code that's running on your computer. E is another way to capture formally the assumptions that we make about the environment in which M runs. Now, what about verifying AI systems? How do we reinterpret E, M satisfies P for verifying AI systems? And again, we need to raise the bar. First, let's reinterpret M. M can still be a piece of code, but more likely, M is a component of an AI system that is learned by a machine or a machine-learned model. So what's different here is that for a computing system, it was a human being who produced the code. For AI, it's a machine that produces the code. That's already one difference. Now, P is going to be one of those trustworthiness properties I mentioned earlier for AI systems, not just safety and security and reliability for computing systems, but properties like robustness and fairness and interpretability for AI systems. Expressing P, those new kinds of properties, will very likely need new kinds of languages, new kinds of logics, probabilistic or stochastic in nature. And finally, we have the double turnstile that connects M and P. And here again, we may need new kinds of logical frameworks to allow us to reason about M and P. We may need new kinds of algorithms to do that reasoning because we're operating over continuous variables or reals, not just discrete variables or Booleans. So interval analysis allows us to reason over intervals of reals. And the most important difference between verifying a traditional computing system and verifying an AI system is D. D is the analogy to E in the traditional verification of computing systems. D here stands for the data, the model of data that we use to test and train the model M, but also the D stands for the data seen by the machine learned model that it's never seen before. The real world data that the model sees or the AI system sees when it's actually deployed in practice. So there's a challenge here of how do we specify D? How do we specify the model of D in a formal way? We could, for instance, use stochastic processes or a distribution that generates the data inputs on which M's outputs need to be verified. But this is a research question, a research challenge. So in a nutshell, when I say, let's try to use formal methods to verify that an AI system is trustworthy, this captures succinctly what I mean. And now what I'd like to do is walk through how we would tackle this from a research point of view. What are some of the open questions and what are some of the technical challenges that arise in the context of trying to use formal methods for AI systems? As I mentioned, there are already two main differences I want to highlight. The first is the need for probabilistic reasoning, and the second is the role of data. And for this talk, I'm only going to talk about two aspects of the role of data, specifying the unseen data and what do we quantify over, to show that there are new questions that are raised by trying to use formal methods for AI. So let's start with the argument for why do we need probabilistic reasoning? And first, let's look at M. M, remember, is different from a typical computer program. You can think of M as a deep neural network, a very large graph with lots of nodes and lots of edges in between the nodes and layers of nodes with edges connecting the layers. M is semantically and structurally very different from a typical computer program. M is inherently probabilistic because internally the model itself operates over probabilities and outputs results with assigned probabilities. So The model itself operates over probabilities, spits out probabilities. It's inherently probabilistic in a way that a typical computer program is not. Structurally, I already alluded to this difference. M is generated by a machine and unlikely to be human readable. On the other hand, in computer science, we're very good at looking at generating what we call intermediate code that machines generate and humans can't read very well. And this intermediate code is something that we're also very good at analyzing using techniques like static analysis and dynamic analysis of code. So it gives me some hope that we can come up with new techniques to reason about this new kind of intermediate code. A machine learned model is usually placed in a real world situation where there's a lot of uncertainty about M's environment. And the only way we know how to represent uncertainty mathematically is through probabilities. What about P? P, interestingly, may be formulated over continuous, not just discrete domains, and or using expressions from probability and statistics. So the very expression of the trustworthy property that we care about, whether it's fairness or robustness, may require probabilistic reasoning, and in fact may require reasoning over continuous domains. So for instance, robustness properties for deep neural networks are characterized as predicates over continuous variables. Fairness properties are characterized in terms of expectations with respect to a loss function over reals. And the only formal notion that we have about privacy is called differential privacy. And differential privacy is defined in terms of a difference in probabilities with respect to a small real value. So even the expression of P requires probabilities, continuous domains, very different from predicates in the past where we express a trustworthiness property in terms of Booleans, and the answer would be true or false, yes or no. And finally, the logic that ties M and P together will very likely need to draw on probabilistic logics and hybrid logics. Now, the good news is that the formal methods community has been working on probabilistic logics and hybrid logics for decades. So I believe that we need to revisit them and possibly scale them up and invent new verification techniques that can work over reals and nonlinear functions, probability distributions, stochastic processes, and so on. Now, what about the role of data, D? I first want to distinguish between what I call available data, data at hand used for training and testing the model, and unseen data, data over which M needs or is expected to operate without having seen it before. Now, here's the first technical challenge: specifying unseen data. The computer science and formal methods community has never had to do this before. So now there's a new research question on how do we specify D? How do we specify D, or maybe just characterize the properties of D? Well, one approach is to specify D as a stochastic process or data distribution, for instance, via its parameters. So for a normal distribution, you might specify it in terms of the mean and the standard deviation. One can think even more grandly and use a programming language to specify D. So for instance, there are probabilistic programming languages that have been invented Perhaps the most widely used one is called STAN. And we can use a probabilistic programming language to write a probabilistic program that actually stands for a statistical model. So we can use this program to stand for the specification of D. I'm really suggesting all of this. No one has done this. This is why these are research questions and research directions. But the real rub is real-world data. What of large real-world data sets that don't fit common statistical models, the ones that you see in your textbook, or which have thousands or millions or billions of parameters? You can't easily just write a specification down for D for those kinds of data sets. Yet these are the very data sets that large language models are operate over and train on. And all of a sudden, we are in a world that the technology has caught up or has surpassed where we are in the science. Now, there's another peculiarity that is a bit of a conundrum, and there's a potential circular reasoning which we need to break. So here's how the argument flows. To specify unseen data, D, we need to make certain assumptions about the unseen data. This is common practice in any approach using formal methods. To specify X, we need to make some assumptions about X. But then would these assumptions not then be the very same assumptions as those we would make to build the model M in the first place? And that sounds circular. Another way to phrase circularity is, how do we trust the specification of D? Remember, our point of this exercise is to say, how can we trust M? Or, in fact, how can we trust the AI system that M is representing? But now I've pushed the trust to, how can we trust D? So how do we break this circular reasoning? Well, one approach, and by the way, I don't know the answer to this question. One approach is use a completely different set of tools outside of formal methods, outside of computer science. Perhaps a repertoire of statistical tools can help us look at D and ensure that we have the specification of D right. Another more common approach within formal methods is to assume that we have a small initial specification, and it's small and simple enough that we can eyeball it, manually check it by inspection, be confident that it represents the D we want, and then use that specification to bootstrap an iterative refinement process to build up a larger and larger specification of D that represents a larger and larger D. This technique is akin to a technique in formal methods called counterexample guided abstraction and refinement. And finally, I've just talked here about specifying unseen data. We also need to relate, how does the specification of unseen data relate to the specification of the data on which M was trained and tested? Here's the second technical challenge. Again, I don't have answers. I only have questions. In traditional formal methods, we strive to prove for all X, P of X. So in traditional formal methods, if X stands for an integer variable, I am going to prove for all values of that integer variable, I will show that P holds of X, of that value. And if I prove it for all integer values, then I know for sure that any integer value that is taken on by that variable x upon execution of the program, P will hold. I'm fully confident that P will hold because I basically overproved what I needed to prove. The same thing is true as if I'm running a concurrent or distributed system and I'm trying to prove for all executions of the system, P holds. So I might overprove and say for all behaviors of M, which stands for the computing system that I want to show satisfies a particular trustworthiness property, I'll show for all possible behaviors, knowing that any one behavior that is reached through the execution of the system, P will hold. Now, for AI systems, the world is a little different. We do not expect M to work for all input data or for all data sets D. So we can't say for all x P of x. That's too strong a statement. That's not to say that if we can't say it, then we're in good shape. But in reality, it's more likely that we can't hope to prove for all x P of x. So what do we quantify over? What do we do? Well, let's divide this expression for all x P of x into the quantification part and the property part. So P of x is the property specification. It represents a fairness property or a robustness property. And for all x represents the specification of data. And we have, two extremes in traditional formal methods where we prove for all x or we prove for some x. Now, for AI systems, we already know that we're operating over data distributions. And so we might replace that with for an x drawn from a distribution for all distributions. That would be a very nice property to show. Or for an x drawn from a given data distribution. Now, just to be concrete, robustness properties very nicely fit into the category where we might say for any arbitrary norm-bounded perturbation, which would be the for all D here, if I change any pixel, I can assure that the classifier will still be robust to that change. That's a very strong statement. It's something that we know how to do for certain kinds of perturbations and for certain kinds of objects like images. So robustness, I have some hope that we can actually use formal methods successfully. Fairness is harder. What do we have? Today, we can, for a given single data distribution, show that for a given fairness property like statistical parity, we can show our classifier is fair. Traditional example that people use in looking at fairness properties and fairness machine learning algorithms is the recidivism data set that was used to show that risk assessment tools used in the US courts are racially biased. So on the one hand, we have robustness, which lends itself to something akin to for all. And on the other hand, we have fairness properties, which lends itself to something more akin to for a given data set. But what we'd like to do is perhaps something in between where we're showing for a class of data sets, P of X holds. So for instance, for robustness, instead of changing any old pixel and saying for any arbitrary norm-bounded perturbation, we might want to say for a particular semantic perturbation or structural perturbation, robustness will still hold. And so the class of distributions would be within the class of semantic or structural perturbations. Similarly, for fairness, we don't want to show a classifier is fair with respect to a single distribution. We'd really like to show that it's fair to not just that distribution, but for nearby distributions. And that would be then the class of distributions over which we would show that fairness holds of a machine learned model. So let me be a little more concrete. I've already alluded to this, but what we like to be able to show, for instance, for robustness in the adversarial machine learning setting, is that M, the machine learned model, is robust to all norm-bounded perturbations D. But more interestingly, we might want to show that M is robust to all semantic or structural perturbations for the task at hand. And now let's consider computer vision. Imagine you have a computer vision system in your self-driving car. And the car is driving itself on the road, and it sees a car in front of it. And there's a dent in the back bumper of the car. Well, you still want the computer vision system to classify that car in front of it as a car, even though there's a dent in the bumper. And a dent in the bumper on an image will not be any old pixels changed. It will be a localized set of pixels that are changed from a normal bumper. So we want the classifier for the self-driving car case to say it's a car, and it's a perfectly fine car. However, if the task is repairing the car in a service shop, then you want the classifier in the service shop to say a repair is needed to this bumper because there's a dent in it. So in that case, that bumper for that car should be classified as it needs to be fixed, not that it's a perfectly fine car. So this is where task specificity comes in. And this is partly what I mean by semantic or structural perturbations. As for different property fairness, we might want to show that the machine learned model is fair on a given data set and all unseen data sets that are similar, for some notion of similar. So a few years ago, some colleagues and I wrote a paper that appeared in Europe to show that if you build a fair classifier, the best fair classifier you can build with off-the-shelf algorithms, then it's very easy to change just slightly the coefficients in the given data set distribution, and the classifier will all of a sudden be unfair. In other words, it's very easy to build a fair classifier that is not robust, that is brittle, that is easy to break with very small perturbations to the input set. So that's not good news. What we'd like is to build a fair classifier once and for all and have it work for a class of data distributions that are close to each other. And that's what we did in this paper. We use an online algorithm to build a fair classifier that is robust to a class of distributions. And it's a very canonical approach in using online algorithms. It's inspired by two-player games. Now, I want to also talk about, I talked about M, I talked about P. I want to talk a little bit about double turnstile, which is the verification task. How do we check the available data for desired properties? For example, if we want to detect whether a data set is fair or not, what should we be checking of the data set? It's not enough always to check what the machine learned model is. Maybe that's too late by then. Wouldn't it be nice if we could detect whether a data set is fair or not? So when we go through the trouble of training a machine learned model, we know it will be fair. If we detect that the property doesn't hold, like a fairness or robustness property, how do we fix the model, amend the property, or decide what new data we need to collect for retraining the model? In traditional formal methods, when we try to prove that a computing system is correct, we actually almost never prove that a computing system is correct. We almost always find a bug in the system. It could be a bug in the model. It could be a bug in the property specification. And the bugs are actually very, very useful feedback to the designer of the system. We call that bug a counterexample. So the question in the AI context is, what is the equivalent of a counterexample in the verification of an ML model, and how do we use it? Another question is, how do we exploit the explicit specification of D, unseen data, to aid in the verification task? And finally, we have some standard verification techniques. Can we, like for instance, over intervals, reals, how can we extend these techniques to operate over data distributions? I want to pop up a level and say I've only talked about an approach of using formal methods, which we in the community would call post hoc verification, where you have a property of interest, you have a model, or a piece of code, and given both, you try to show that M satisfies P. There's another approach where you start with the property of interest, and you construct M iteratively, step by step, always preserving the original desired property P. This is called correct by construction, and we might also call it as model synthesis. I already mentioned that formal methods for AI would likely have to be task specific until we know how to prove things more generally. It's true that generative AI gives us a hint at general AI, but right now, we are still looking at AI systems as being task specific. There's another aspiration that we have in formal methods, which is to do proofs compositionally. That means you have a big system, you prove a property is true of components of the system, and then you infer the property holds of the composition of the components. And so you don't have to reprove the whole big system because you've already done the little proofs. And finally, as I mentioned earlier, there are statistical methods for model evaluation and model checking, which I would encourage the computer science community to pursue by complementing formal methods with statistical methods to validate specifications, be they of the data or the model or of the property. So I'll close here and say that this DM satisfies P is my characterization of how trustworthy AI meets formal methods. Thank you very much.